Thank you very much. We've had lots of questions coming through. The first is from Garth, and he said, "Isn't it true that Einstein was unaware of the Michelson-Morley measurement of the velocity of light relative to the ether?"
I actually don't know, is the short answer. Certainly, it was not crucial to Einstein. I do know that. So for those of you who are not familiar with the background story here, in the mid 1800s, we put together what we call the theory of electromagnetism, especially James Clerk Maxwell, the modern theory of electromagnetism, which explains, among other things, the importance of the speed of light. Maxwell is the one who showed that light is a wave in the electric and magnetic fields. And this was a great triumph. It unified electricity and magnetism. But it seemed to have this special role played by the speed of light. And it seemed like if you naively looked at the equations, everyone would measure the speed of light to be the same. And people were like, well, what is the medium in which light is moving in the first place? So they invented this thing called the ether, the luminiferous ether, as a medium through which light waves can travel. And they thought about how to detect its motion. And Michelson and Morley famously did experiments to detect the motion of the Earth through the ether, and they couldn't find anything. So people came up with increasingly elaborate schemes to make the ether undetectable. And it was Einstein's breakthrough to just say, you're working too hard. You just don't need ether at all. It's playing absolutely no role. You've made it undetectable, okay? But he may or may not have known about Michelson and Morley's experiment, but he was motivated by just the theoretical desire to make a clean, coherent theory of electromagnetism. And he was just really, really good at understanding what elements of the theory were necessary and which ones were not. Whether or not he knew about the data, he certainly knew that the theoretical machinations that people were going through were all in the service of making the ether unobservable. So he just said, throw it out, and it worked.
Nice. We have a question from Danny who said, "Do you ever find yourself thinking like Einstein and complaining that a mathematician is just complicating my physicist view?"
Oh yeah, all the time, because it really does happen. That's the thing. In this case, Einstein was a little bit premature, but mathematicians and physicists have different motivations and they're doing things for different reasons, and that's good. That's a correct thing. Like, mathematicians aren't trying, usually, to explain the physical world. They want to understand the implications of axioms and what theorems they can prove. They want to understand the logical structure of how all of these different things fit together. Physicists care about the one actual world. If you want to slightly oversimplify, mathematicians care about all possible physical worlds, and physicists care about the one actual one that we live in. So, of course, they're going to be interested in different things. In a very real sense, physicists can move much faster than mathematicians because we don't care about proving things carefully. We can just leap to the right answer, even if our mathematical I's are not dotted and T's are not crossed.
Garth has asked, "How do you know that there is only one time coordinate?"
Well, I would notice, when you tell someone to meet them for dinner, you only have to tell them one time. You do not need to tell them two numbers. Now, of course, you can imagine, because this is what theoretical physicists do, imagine there are more dimensions to space-time that are hidden from us. In the case of dimensions of space, we literally do imagine this. String theorists and other people imagine exactly that. If there were more than one dimension of time, then naively, you could move in that dimension. If you have two dimensions to move in, you can go in a circle. If you only have one dimension to move in, you can only go in a line, right? So if you had two dimensions of time, then naively, time travel would be easy. You could just zoom around in a little circle, okay? And as far as we know, we can't do that. Now, I'm trying to speak carefully because maybe there's a version of the theory where there are two or more dimensions of time that somehow prohibits you from easily doing time travel. I don't know, but we only need one time dimension to explain the world that we see, so that's good enough for me.
Florian has asked, I lost which slide this was, but I hope you understand. You have GYX and GXY, but not GTX and GXT. Is there a special reason for this difference in symmetry?
No, they're all there in principle. In the real world, some of them might be important for some situations and not others, but the metric tensor G mu nu contains GTT, GTX, GTY, GTZ, all the possible combinations. I do not mean to leave any out. I just didn't want to write them all down.
Thank you. Leanne has asked, I think it's the Riemann curvature. Wouldn't simplifying the R lose too much to make the remaining data useful?
Well, you have to worry about that, but in fact, no. So basically what happens is, of course, I didn't have as many hours as I would like to explain everything to you, so I skipped over some details. In the Riemann tensor, even though it's 4 by 4 by 4 by 4, so 256 entries, there's actually a lot of redundancy in those entries. As it turns out, there's only 20 independent numbers that go into making the Riemann tensor. Still a lot of independent numbers, but still only 20 of them. When you boil it down to the Ricci tensor, the Ricci tensor turns out to have 10 independent quantities. So it's literally containing half of the information that's in the Riemann tensor. And it turns out that the other half is also important, but you can derive an equation for that other half also. You can actually derive it from Einstein's equation. You don't need a separate equation to do it. And that other equation basically talks about the propagation of gravitational waves. Because if you think about it, Einstein's equation is telling you what happens because of matter and energy in the universe. But you can have a gravitational wave passing through space-time even without any other matter and energy. So the other components of the Riemann tensor are crucial to explain those.
Thank you. Cass has asked, any hot takes on reconciling general relativity with quantum field theory?
Yes, but they're probably too long to get into in great detail here. So quantum field theory, for those of you who don't know, is our best current way of talking about fundamental physics. Particle physics, the Higgs boson, all that stuff falls under the rubric of quantum field theory. Quantum field theory is not a replacement for quantum mechanics, even though it's sometimes talked about that way. It is a version of quantum mechanics. It is under the umbrella of quantum mechanics. So what we're really trying to do is reconcile general relativity with quantum mechanics, just like Einstein needed to reconcile Newtonian gravity with special relativity. And just like Einstein, what he did was, he didn't just add a constant or a new term to Newton's equation. He threw out Newton's equation and derived something completely different that reduced to Newton's equation in the right circumstances. So what I think, and what almost everyone thinks, is that we're not just going to modify general relativity, we're going to have to come up with a completely new theory that includes quantum mechanics and reduces to general relativity under the right circumstances. Now, I don't know what that theory is. I have some ideas about it. String theory is another idea about it. Loop quantum gravity is another idea about it. I think that one of the important insights is that it won't be quantum field theory. It'll be quantum mechanics, but we'll have to move beyond the paradigm of quantum field theory.
Oliver has asked, if one twin stays still and the other goes close to the speed of light, since velocity is relative, why doesn't the first twin age faster than the moving twin?
Good. Well, the answer is because one comes back. So if both twins moved on straight lines for their entire history, there would be no way to say one was younger and one is older, because they would only meet at the beginning point of their journey. They would never come back to compare clocks, right? What you can do in general relativity is compare the amount of elapsed time along trajectories that both begin and end at the same event in space-time. In the case of the two twins, their journeys are not symmetric. One is never accelerated, and the other is accelerated. So it's very easy to tell which one goes the shorter distance path.
P has asked, can you be absolutely sure that C has been constant throughout time, and in particular in extreme physical and gravitational environments?
I am not absolutely sure of anything. I'm not absolutely sure that any of you even exist, and I don't live as a brain in a vat and being, hallucinating all this, right? So absolute certainty is not the standard to which scientists ever aspire. What we do is we make hypotheses and we test them and we assign credences to them. So we, of course, hypothesize maybe the speed of light is constant, maybe it's been changing, and then we go look for data that would talk to us one way or the other. So far, all of the evidence we've ever collected from astrophysical experiments, ground-based experiments, things near the Big Bang, all the evidence is that all of the constants of nature that we've measured are the same in extreme environments throughout the universe. A new experiment could come in tomorrow that says something different, but that's what we've seen so far.
MRG has asked, how is the black hole image we have looks like an image from top angle, whereas we exist on one side of the spiral arms?
Well, we see what we can see, right? So the black hole is a sphere. There's no such thing as a top. It's perfectly spherical, or almost perfectly spherical. It's actually spinning, so it's a little bit oblate. But we're going to see light rays that go around it toward us, right? If something is right behind the black hole, its light rays will just go into the black hole. We won't see it. So when we look at a black hole, we will generally see a black spot surrounded by light.
Mario has asked, when we define hypersurfaces of simultaneity in SR, testing my words, it seems you are defining them retrospectively. They are in the past. What is your view on this? And how can we say the present is described by an object we can only define retrospectively?
Well, I don't think it's true that we only define them retrospectively. We can easily define what we mean by surfaces of simultaneity in the past, present, and future. But what I would actually say is, there's two ways of thinking about relativity. One is that one's choice of how to divide up space-time into space and time will be different for different observers, can be different and will be different. That's a perfectly valid way of saying it. Another way of saying it, which I actually prefer, is dividing space-time up into space and time is just a convenience when it's convenient. It's not anything fundamental. It's not built into the fabric of reality. Just don't try to think about things that are simultaneous if they're far away from each other. Don't try to compare which is first, which is later. That's going to be dependent on what coordinate system we use. Therefore, it can't be a fundamentally true thing. Focus your attention on things that are measurable and observable, which are things that are happening right next to each other. So that's why in the twin experiment, it is crucially important that the twins start at the same point. One of them zooms out, but they come back to the same point so they can compare their clocks right next to each other.
Thank you. Srivatsava has asked, they're moving. In the pictures of Einstein's field equations I have seen, there is an additional term on the left side, like lambda times metric tensor. Could you please explain it?
Sure. When Einstein in 1917 realized that his equation predicted that in cosmology the universe should either be expanding or contracting, he went to his astronomer friends and said, hey, is the universe expanding or contracting? And they said, no, the universe is pretty much the same from moment to moment in time. So he tried to modify his equations by putting in a new term which he called the cosmological constant. That's the lambda times the metric tensor. And then later, in the 1920s, 10 years later, we realized, oops, the universe is expanding. And Einstein was like, no, I missed my chance to predict the expansion of the universe. These days, we know that there is actually a non-zero cosmological constant that was discovered in 1998, but it's small and it's not stopping the universe from expanding. But we also know that you don't have to call it out as a special term all by itself in the equations. You can bundle it up as part of what we called the energy momentum tensor. The cosmological constant is just a way of talking about the energy density in empty space, the energy density that is inherent in space itself rather than in stuff like stars or gas or whatever. So the cosmological constant is in the equation I showed you. It's in the term T mu nu.
Nigel has asked, why is G constant under all conditions of space-time?
Well, again, it doesn't have to be. We've tested that. We've imagined theories. People have written down theories. Famously, Karl Brons and Robert Dicke invented a theory where Newton's constant would change over time. Famously, Paul Dirac hypothesized that it would change over cosmological time. But then we go make measurements, and it seems to be the same. Now, in retrospect, that kind of makes sense. If you have the way to make Newton's constant change with time is to make it be influenced by some field in the universe, like the Higgs field, like the electron field, etc. But those fields generally settle down and stop evolving pretty quickly. That's why the Higgs field was so hard to detect in the first place. So even if Newton's constant can change by a little bit, it's not surprising that no change is visible to our observational capabilities.
Florian has asked, in the light of the Nobel Prize in Physics for quantum mechanics this year, do you think that quantum computers will help us solve more scenarios for the Einstein equation?
Oh, I really don't have any idea. I mean, that's a perfectly legitimate question. We won the Nobel Prize for quantum entanglement. Not we, I did not share in it, but a very good set of physicists won the Nobel Prize for experimentally demonstrating the reality of quantum entanglement and the fact that quantum entanglement behaves exactly like quantum mechanics says it should. Now, those facts are crucially important for building quantum computers. In case you don't know, we have built quantum computers. They're just tiny ones. They're not very much better than a pocket calculator. So what will quantum computers do in the future is actually an ongoing research problem that is very hard to say. It seems like there are certain kinds of problems for which quantum computers are especially well suited, mostly simulating quantum mechanical systems like molecules or chemistry or something like that. Big classical things like general relativity in spacetime might not see any improvement from putting on a quantum computer, but maybe there's some clever way of doing it that I just don't know about.
Well, we shall see. Garth has asked, do you have an explanation for the arrow of time?
I do. The arrow of time is because entropy is increasing. Entropy is the way that we have of measuring disorderliness in the universe. High entropy is all messy and disorganized. Low entropy is very organized. And in the early universe, near the Big Bang, the entropy of our universe was very, very, very small. So small that in the last 14 billion years, it's been increasing and is still nowhere near its maximum value. So that's where the arrow of time comes from. There's a difference between the entropy of the universe in the past versus the future. Now, what we don't know is why the entropy of the universe was so small near the Big Bang. That's still a mystery.
And Ian has asked, how do gravitational waves propagate?
Oh, well, I'm not sure exactly what kind of answer would satisfy you. They propagate at the speed of light, almost exactly the same way that light waves propagate. So light waves are waves in the electromagnetic field. So there's a field of the electrical field, there's a separate field of the magnetic field, and when you poke it a little bit, when you perturb it, there's ripples that go out. The field here sort of tugs on the field right next to it and makes it go up, and those tugs propagate outward at the speed of light. Exactly the same thing is true for a gravitational field, but as you now know, rather than electricity or magnetism being the field that is carrying the information, it's the metric that is carrying the information. So the metric gets stretched by a black hole spinning or whatever, and that pulls the metric right next to it, then right next to it, and that propagates outward at the speed of light as a gravitational wave.
Jessia and Lee ask, what is your opinion on the holographic principle? Is it a convenient mathematical tool, or does it reflect something physical about reality?
I think it reflects something physical about reality. You know, after we came to accept the existence of black holes in the 1960s and 70s, Stephen Hawking famously showed that black holes give off radiation in the 1970s and have a temperature and have an entropy. And this led to a puzzle, like if you throw a book into a black hole and the book is full of information and the black hole just evaporates away, is the information destroyed? Many physicists want it not to be destroyed, so they think that somehow that information has to get out, hidden in the radiation. And this has led to the idea that all of the information contained inside the black hole can be thought of as distributed across the horizon. So rather than being embedded inside, which is one way of thinking about it, which is perfectly fine, you can also think about it as being located on the two-dimensional horizon. This is called the holographic principle because the horizon of the black hole, the boundary of it, is one dimension lower than the interior volume of it. And in fact, we now know of very explicit circumstances under which the holographic principle is realized in quite a mathematically careful way. We're not yet sure all of the ways in which it's realized or whether it plays out in completely general circumstances, but we're hopeful that it does.
James has asked, can gravitational waves have an analogy of redshift?
Oh yes, absolutely. Waves traveling through space, whether they're gravitational or electromagnetic, can be redshifted or blueshifted. You know, in many, many ways, in almost every way, I would encourage everyone to think of gravitational waves much like electromagnetic waves. They're very similar phenomena.
P has asked, what are your ideas on dark matter and dark energy, and do those change or affect the math?
They don't really change or affect the math. It's pretty easy to take dark matter or dark energy and say that, look, they have energy, therefore they're part of the energy momentum tensor. They're on the right-hand side of Einstein's equation. We already know what the math is. The question is a physics one. What is the physical origin of these things? Dark matter is some kind of particle, some kind of matter substance that we haven't yet detected here in laboratories on Earth. That's not that hard to believe, honestly. Like, who says that all the particles in the universe have to be easily detectable by we human beings? In fact, there's more than enough candidates for what the dark matter could be. The question is, which of them is the right one? And we're not sure yet. The dark energy is in some sense even easier. You know, Einstein had this idea in 1917 that there could be energy in empty space, the cosmological constant. And that fits the data perfectly, that the dark energy is the cosmological constant. We invent other alternatives simply because we want to keep our options open, but the data is perfectly happy with the dark energy being the cosmological constant.
Andy, first of all, said thanks for the really amazing talk, which a lot of people have said, so thank you. He says, you're a great science explainer. Any tips for someone interested in science communication?
Well, I think that, you know, what keeps me grounded in science communication is assuming that the audience is smart and interested, but they are not experts. They have not heard these words before, right? They're not familiar with these concepts. And when you personally learn some concepts, it's just easy to forget what it was like to not have known them, you know, to know that a vector has a direction. That's just like an obvious thing. That's what vectors do. But if you're not familiar with it, you can easily forget that some people might not know it. So it's really a non-trivial skill to remember what other people know and don't. And in fact, you're not going to do it successfully just by thinking your way into it. Talk to people and figure out what it is they know and don't. You know, one way of putting it is that I learned this the hard way. If you give a talk on some topic and you give it multiple times, and every time you give the talk, you get the same question at the end, why aren't you answering that question during the talk? There's clearly a question everyone has. So think about what are the questions that people have and try to answer them.
It's very good advice. Luminaire Arts have asked, what would you like to win a Nobel Prize for?
Oh, what would I like to win a Nobel Prize for? You know, that's a slightly different question that I usually get asked. So that's a very good one. You know, the Nobel Prize is usually given for either doing an experiment that discovers something or shows something is true, like the most recent one. These are experimentalists. Or theorists who come up with a theory that predicts something very, very specific, which then gets tested experimentally, okay? An exception is Roger Penrose, who recently won the Nobel Prize a couple of years ago for a theorem and a set of theorems basically saying that black holes will almost certainly be produced in the real world. But usually you make a specific prediction that gets tested. I have a couple theories that I've suggested in papers, which in principle, they could be tested experimentally and shown to be correct. But honestly, it would just be a matter of me getting lucky. It's not just because these theories have an aura of inevitability about them. What I would like to win the Nobel Prize for is an insight into how things fit together in the nature of reality that, you know, no one has ever had before, and that once you have, you just go, oh yes, it sort of had to be that way. That's what general relativity was like. Like once Einstein said it, everyone's like, oh yeah, that's genius. Of course, it had to be it that way. I have no such good ideas right now, but I'm not done yet. I'm still trying.
If you have those ideas, you know where to bring them. We'll
I'll
happily hear
let
you
you
speak
know.
about them. Exactly. Well, that looks like, oh, sorry, I've got one more question. Garth said, could we know whether we are living in a black hole?
Yeah, we're not. We're actually living in what is much more like a white hole. If you've ever heard of white holes are just black holes played backward in time. So a black hole is a region of space-time where gravity is so strong that once you enter, you can't leave. And furthermore, in a simple black holes can be complicated, but in simple cases, once you enter, there is a singularity that you will inevitably hit. In a very real sense, that singularity is in your future. If you think about it, we don't know of any singularities in our future. We're not forced to hit any singularities in our universe. But we came from a singularity in the past, the Big Bang. So our Big Bang cosmology is actually mathematically quite similar to a time-reversed black hole.
That actually linked to the other question that popped up because Denise said, any thoughts on white holes?
Yep, we live in one.
Excellent. So that seems to be all the questions that have come through. A lot of people saying thank you very much for the talk, brilliant, energetic, and easy to follow. And I'm going to say, before thanking you, Sean, I'm going to say thank you to the audience for watching and bringing, as usual, your fantastic questions. Glad you could make it. If you do want to do this suggested donation of £10 to support the live streams and our live streams in the future, please do, but no pressure. Don't forget, you can also buy copies of The Biggest Ideas in the Universe, Space, Time and Motion now. Some of you already said you have, so thank you very much. Thank you very much, Sean, for doing a fantastic talk, and goodbye to everyone that's watching.
Bye-bye.